Now we are going to start talking about connectedness. And I thought before I gave you the precise mathematical definition of connectedness, we'd spend a few minutes trying to build up our intuition. So here we've got two sort of stylized maps. One is showing Arkansas, one is showing Hawaii. And I don't think any of you would disagree with me that Arkansas, or at least the map of Arkansas, is connected and Hawaii is not. And what do we mean by that? Well, notice that Hawaii has these 6 pieces, has a bunch of pieces on this map. We are seeing 7 of them. So Hawaii breaks up into these 6 disconnected pieces, and Arkansas doesn't really break up like that. Now let's think about this for a minute. It's not that Arkansas doesn't have any smaller pieces, any smaller regions. You can pick out something like, for example, here is Washington County, is the county in Arkansas that Fayetteville is in, that we're all in right now, or at least that I am, that the university is in. And so it's not that Arkansas doesn't have any smaller pieces, but look at this. The county of Fayetteville in here, the Washington County in here, it's got a boundary. It's there. There are points that are near to Washington County and also near to the rest of Arkansas, to some other county. And if we go back to Hawaii, these 6 pieces, these 6 islands, there aren't any boundary points. There's no points, at least on land, that's close to the big island and is also close to Maui. So there's no pieces that's close to either of them. And let's recall our Proposition 5.3.7c says that X is in the boundary of a region A if and only if for all r greater than 0. We have that ball centered at X of radius r contains a point in A, and that ball also contains a point that's not in A. So the boundary of a set, the way we've defined it, the boundary is all the points that are close to Washington County, but also close to the rest of Arkansas, the stuff that's not Washington County. So we say that a set or a metric space is connected if every subset is like Washington County. There's at least some points that connect Washington County to the rest, some points that are close to Washington County and also close to everything else. And we say it's disconnected if it's like Hawaii, if there are some regions such as Big Island that are separated from the rest of it. There's no points that are close to both Big Island and to Maui. So let's write down the formal definition of connectedness. So let's let XD be a metric space. And then we say that X is connected if every subset of X has a boundary point, if we don't have any Hawaiian Islands that are off on its own. If whenever A is a subset of X and the boundary of A is empty. Now hold on a second. The empty set is a subset of X, and the empty set certainly doesn't have a boundary. So we can't say no subsets of X have empty boundary. The empty set has empty boundary. And there's one other subset of X that always has an empty boundary, namely all of X has an empty boundary. There are no points in X where you can put a ball around them and get a point not in X. The ball is contained in X. You're thinking of X as the whole universe. So there's no boundary to the whole universe, at least not in metric spaces. There are no points that are close both to the universe and not the universe. So there are two possibilities. There are two sets with no boundary. We say X is connected if those are the only two subsets that have no boundary. And it's sometimes useful to have equivalent ways of writing connectedness. So let's recall we said in an earlier video that the boundary of A is the closure of A minus the interior of A. And we've also got that the interior of A is contained in A, which is in turn contained in the closure of A. So the boundary of A is empty only if A is equal to both its closure and its interior. And A is equal to its closure if and only if A is closed, and A is equal to its interior if and only if A is open. So a set has no boundary. Its boundary is the empty set. That means the closure must equal the interior, which means they must both equal A, which means that A has to be open and closed. So the boundary of A is the empty set if and only if A is both open and closed. There's another characterization of boundary. That is the closure of A intersect the closure of X minus A. So if A and its complement and X minus A are both closed, then the boundary of A is empty. So if you can break X up into two closed sets, then it's disconnected. A little bit more work, you can show that if you can't break up X into two closed non-empty sets, then it is connected. But you can prove that. So I'm going to write out a proposition that says the following conditions are equivalent, where one of them is the definition I've given for being a connected metric space. And then the following statements are equivalent. So the first one is that if A is a subset of X and A is both open and closed, then A is either X or the empty set. Those two subsets are always both open and closed and have no boundary, but connectedness means those are the only two like that. So let me write out the empty boundary condition as equivalent to the Clopin condition. And the third option is where you write X explicitly as two pieces. If X is A union B, where A intersect B is the empty set, A and B are both open. If you can write X as the union of two open sets, then either A is everything, B is nothing, or A is nothing, B is everything. And that's also true if A and B are both closed. If A is the union of two disjoint closed sets, then it's as before, either A is everything, B is nothing, or B is nothing, or A is nothing, B is everything. And you can pass between, you can prove the equivalence pretty easily. Yeah, A and B are equivalent because you have no boundary if and only if you're open, and then parts C and D are equivalent. You just notice that A is the complement of B, so if A is open, B is closed. If A is closed, B is open. And if A is open and B is also open, that means A is the complement of an open set. It's closed, so it's Clopin. So you can think of connected sets in this number of different ways, as having a subset with no boundary, which means a subset that's not attached to the rest of it, or as you can break it up into two different pieces. Let me go ahead and write out the contrapositive to 5.6.2. So, first statement is that there is a Clopin set with A both open and closed, that is neither the empty set nor the entire metric space. Part B is there exists an A subset X with no boundary and which is neither empty nor the entire metric space. And then the break it up into two pieces is that there are two closed sets F1, F2 in X, such that F1 is not the empty set, such that neither of them is empty. They are disjoint, which means that neither of them can be the entire set because there's always got to be some points not in the other one. And X is F1 union F2. Similar statement for open sets. Two open sets, neither of them is allowed to be the empty set. They are disjoint, and X is, and the two of them together make up all of X. And I'll go ahead and state explicitly that this is equivalent to X is not connected. So this is the negation of everything we saw before. There is one more definition I want to say. You remember that in section 5.5 we defined what it meant for a subset of a metric space to be compact, not only the entire metric space. Well, you can do the same thing with connected sets. And then we say that E is connected if the subspace E, comma D is connected. So if you can find relatively open sets, for example, two relatively open sets whose union is all of E, then E is connected. And on your homework problem, you will explore a little bit more of what a connected subset of a larger metric space, what that looks like. The next thing I want to prove is an unsurprising proposition. It says that if you're in the real numbers, you're connected if and only if you're an interval. So let's recall the definition. Some people use this as the definition of intervals. Some people use the long list of open, closed, half open, infinite. What have you as the definition of intervals? So you can, last semester I made this the definition of interval. It's lemma 1.6 in your book. This says that a subset of the real numbers I is an interval if In the definition, you just say if. For the lemma, you have to also write and only if. Whenever you have 2 points in the set and there's a point between them, we have that C is also in I. And let me just draw this for you real quick. Here is your real line. Then if you're an interval, anytime you've got an A and a B, then you've also got everything in between them. And that's what it means to be an interval. And maybe you've got a little bit beyond B if it's open at interval. Maybe you stop at A if it's a closed or half closed interval. But this is the idea behind what it means to be an interval. So here is the next proposition. Let's let I be a subset of the real numbers with the usual absolute value metric. I is connected if and only if I is an interval. And one direction of the proof, at least, is not hard to write. So first, we're going to suppose I is not an interval. Then there exist points A, B, and C with C between A and B. A and B are both in our interval I, and C is not in I. Then let's let G1 be minus infinity up to C intersect I, and then G2 is C2 plus infinity intersect I. And then let's just check all our conditions in our converse to proposition 5.6.3. G1 and G2, they are open in the real numbers. So by proposition 5.3.5, they are relatively open. In the metric space I by proposition 5.3.5, and remember, relatively open just means open. G1 intersect G2, well, that's contained in the intersection of our two intervals, which of course is the empty set. And A is in G1, B is in G2, so G1 is not empty, and neither is G2, and C is not in I, so I is contained in G1 union G2. You can check the finicky details of that for yourself. And so we've split I into two open sets that they're both open they're disjoint. Neither of them is empty, and their union is all of I, so I is not connected. Let's prove the converse. Let's suppose I is not connected. And then you will show on your homework for this video that there exists sets U1 and U2, subsets of the real numbers. Let's say they're subsets of the real numbers, not I. This is why I'm using the homework, such that U1 and U2 are both open. They are disjoint. Neither of them is disjoint from I. And I is contained in their union. Yes, the letter U is somewhat unfortunate. It looks like a union symbol, but it's the letter I used on the homework, and I had a reason for doing it there, so I think we're stuck with this notation. And that's very confusing, so let's draw the real line again. Now the idea is we've got a U1 and a U2, maybe not intervals, but certainly both open. And they both have points of I inside them. And you can see from this picture that I is now disconnected. We've got two pieces of I. And you'll see on the homework that this is an equivalent condition for a subset of a metric space to be disconnected. So we're going to let A be in U1, B intersect I, and B be in U2 intersect I. And without loss of generality, meaning we could just switch which of the U's is U1 and which is U2, and which of these points is A, which is B. We're going to say that A is less than B, and we're going to let C be the supremum of the following set. We're going to let it be the supremum of U1, then we'll intersect that with minus infinity B. Now, A is in U1, and A is also less than B. So we're not taking the supremum of the empty set. C exists, and C is less than or equal to B because it's the supremum of numbers, because B is an upper bound on the interval from minus infinity to B. Going back to our picture, C is about here. I'm going to make the following claim, and once I've proven it, I will show that it implies that I is not an interval. C is not in U1 and C is not in U2. And here is how we prove just the claim. We'll circle back in a minute to the full-on proposition. So we're going to pick some positive real number. Then C minus R is not an upper bound. On this set, U1 intersect this interval, but C is, so there is an X in U1. U1 intersect minus infinity to be what we only really care about, U1, with C minus R is strictly less than X is less than or equal to C, because C is an upper bound on this set. So the ball centered at C, of radius R, which is, the interval from C minus R to C plus R. If you intersect that with U1, you do not get the empty set for all R bigger than 0, and by proposition 5.3.7, C is in the closure of U1. But all the real numbers minus U2 is a closed set. With the U1 contained in R minus U2. So we have that C is in the closure of U1. That must be a subset of R minus U2. So C is not in U2. In particular, C is not B. So since B is an upper bound on U1 intersect the interval from minus infinity to B, C must be strictly less than B. Let's pick a positive real number again. And let's let Y be C plus then whichever is smaller, B minus C over 2 and R over 2. Y is bigger than C, so Y is not in the thing that C is the upper bound of. Y is less than B. You're adding something that's less than B minus C. So Y is in this interval. So the only way both of those things can be true is that Y is not in U1. So the ball centered at C of radius R contains a point, the point Y, which is not in U1. So this ball is not a subset of U1 for any positive radius R. And remember, we saw that open sets, every point in an open set has a ball around it. So we have that C is not in U1. because U1 is open. Now, A is in U1 and is less than in B. So A is less than or equal to C. B is an upper bound. On this interval. It's an upper bound certainly on U1, so it's an upper bound on U1. Intersect this interval, so it's less than or equal to, it's greater than or equal to the least upper bound. But A is in U1, B is in U2, C is not in either of them. So we must have that A is strictly less than C is strictly less than B. Also, A is in I, B is in I, and C, we've proven, is not in this union. And this union contains I, so C is not in I. So I is not an interval. That completes the proof. Now let's prove a result about continuous functions and connected sets. So we start with two metric spaces. We're going to start with a subset of the first one, and we're going to take a function from the subset into the second metric space. And let's specify that this is a continuous function. And then the conclusion of this theorem is that the image of the function, that's the set of all f of e such that e is in our set E, is connected. Not always, as long as E is connected. And the proof is pretty straightforward. It follows from theorem 5.4.3. First off, let's let y be f of e. Notice that ed and y rho are metric spaces. And f, you can think of f as going from e to y, is a surjective continuous function. So we're not going to use the metric spaces x and z at all. We'll just work in these subspaces that are the domain and image of f. So we don't have to deal with the connected subset business from your homework, at least not in this proof. Now, assume E is connected I am tired of writing out connected, so you'll just have to deal with an abbreviation. And let A be a subset of Y, and let's suppose that A is not the empty set and A is both open and closed. And we're trying to prove that Y is connected. That means we're trying to prove that the only non-empty Clopin sets are the entire space. So we're trying to prove that A is in fact all of Y. And how are we going to do this? By theorem 5.4.3, F inverse of A is, well, obviously that is a subset of E. That's the set of all x in E such that f of x is in A, which by definition is a subset of E, is both open and closed. E is connected, so we have that F inverse of A must be either the empty set or it must be all of E. And we assumed A was not empty. So there's some element in A of A, and since F is surjective, so there must be some x in E that maps onto whatever particular element of A is. So F inverse of A is not the empty set. Then, so F inverse of A is E. That means that if X is in E, then F of X is in A. But F is surjective, F of E is all of Y. Every point in Y is an F of X for some X in E, so that means every point of Y must be in A, so Y is equal to A. And this is true for all Clopin sets. They're either the empty set or they're all of Y, so Y is indeed connected. And if we put this together with the last theorem, theorem 5.6.3, we get the intermediate value theorem. So let's let XD be a connected metric space. And F, a function from X to the real numbers, be continuous. You do need it to be a function into the real numbers, not into a general metric space. We are using the special properties of the real numbers. And then we'll suppose we take 2 points in X, and we'll suppose that there is some c between f of x and f of y, where c is a real number. Then there is a z in our metric space such that f of z is equal to c. And the proof is just 3 results we've already proven. So the image is connected, but to f of x, f is a function to the real numbers. So by theorem 5.6.3, f of x is an interval. And so by the definition of interval, or lemma 1.6.6, c is in f of x, and that means c equals f of z for some point z in x. And that is all there is to that.